Okay, so our next foray into acids bases is dealing with a titration. Now we've done titrations before. I don't remember if you may have even done one in lab. Did you do one in lab where we did? I'm not remembering this year if we did it or not. Because generally we would do one in the fall, at least as an introduction, at least playing around with burettes. I'm not sure how I'm going to get to do this yet. There's only 9 of you coming out of the 20 to actually physically coming to class. But I found one online that's very much related to the physical manipulation of burettes, but it's kind of tedious, and I haven't decided if I want to subject you to it yet or not. I don't know. I'm still working on it. Anyway, here's the background. So it's not unrelated to what we've been doing. We're now going to go back to stoichiometry and see where stoichiometry fits into all of this. And as I said from the start, if you're good at stoichiometry, it helps, a lot of different topics. All right, so the weak acid HNO2 is titrated with the strong base. What all that means is it's reacted with. So we do a analytical method called titration, where you use this burette, which gives you a very accurate measurement of volume, and you can do it drop-wise. So you can do like 0.01 at a time. All right, so the reaction is it's double replacement, and we get Na, NO2, and HOH, which on the right-hand side, we could rewrite it as water, H2O. Now, the net ionic equation would be this is a weak acid, and weak acids are written in their molecular form, but that's a strong base. So that ionizes. Soluble salt. How do I know it's soluble? It's sodium. Sodium is group 1, all group 1 metals. And then water is a covalently bonded molecule, so it does not ionize. So we do have a spectator ion involved in the reaction here, and that would be Na+. So what could be substituted here is any strong base. Now this particular one though reacts in a 1-to-1 ratio. So 1-to-1, that's important. All right, so if 10 moles of HNO2 reacts with 3 moles of NaOH, which substance is the limiting? By this point in your chemistry life, you should be able to easily tell me which one is. It is a 1-to-1 mole ratio. What that means is for every 1 mole of one, 1 mole of the other one reacts. So if you start with 3 moles of NaOH, which really is 3 moles of OH minus, because it's a 1-to-1 ratio there too. So 3 moles of this and 10 moles of this, well, all 3 moles are going to be used up. So at the end, there's going to be 0 of this left. Now we can't do an ice chart with this because remember, E stands for equilibrium, and this is not equilibrium. But I will sometimes show you this and change the equilibrium to the end result of the reaction. So at the end result of the reaction, because then the change goes by the stoichiometry. This is minus X because it's 1-to-1 ratio, minus X. This would be plus X and plus X. Now what is X? Now with an equilibrium, we have to do the whole K and write the expression. But with this, we don't. It's literally stoichiometry. So one of these is going to stop the reaction because it runs out. So the minus X will always be equal to the one that is the limiting, which is the one you have less of. Now, tricky part, when it's a 1-to-1 ratio. But remember, our mole ratio so far with acids have all been 1-to-1. So in other words, this minus X is actually minus 3 moles, and you don't have any of that left over. So minus 3 moles, you have 7 moles of this left over. And then we're making 3 moles of that and 3 moles of that. So we're making 3 moles of NO2 and H2O. There's none of this left over, and we have some HNO2 left over. So what exists in the solution? You have HNO2, you have NO2 minus, and you have water. Now notice what this right here is. We have the weak acid HNO2 and its conjugate base NO2 minus. So that's a buffer solution. So what we're going to do is look at the effects of a titration in terms of a buffer solution as well and getting pH. All right, so first of all, though, calculate the pH containing of a solution only 0.2 molar HNO2. So if we have HNO2 all by itself, that's an acid, it's a weak acid. You get H3O plus and you get NO2 minus. So we have to do an ice chart. Now this one's not a buffer because you don't have any of this or any of this. So this starts out at 0.2, we don't care about water, minus X. 0.2 minus X. plus x and plus x, x and x. I'm going to skip ahead to the k expression, which would be Ka equals products x times x, or H3O plus times NO2 minus, over 0.2 minus x, ignoring the minus x like we always do. I didn't share my calculator, but I'm doing it up here on my screen. I can see it, times 4 times 10 to the minus 4. And then we got to, that equals x squared, so we got to take the square root, and we get x equals 8.9 times 10 to the minus 3, which gives us a pH of, now that equals the H3O plus. So then I just take the negative log of that answer, and we get 2.05. So this thing has a molarity of 2.05. All right, so far so good. Next one. Now we're calculating the pH if it only had NaNO2. So that is not an acid or a base, it's a salt. It's going to ionize. It's going to get you Na plus and NO2 minus. Now out of those two, which one affects pH? Well, NO2 minus does, not Na plus. That's the conjugate acid of the strong base NaOH. So NO2 minus added to water, HNO2 and OH minus. Notice it's a Kb, we have a Ka. So I'm skipping ahead a bit. So 1 times 10 to the minus 11. The Kw divided by 4 times 10 to the negative 4. And we got 2.5 times 10 to the minus 8. 2.5 times 10 to the minus 8 equals x times x. Right, so we had 0.175, the initial, the change, the equilibrium, minus x, same as always, x and x. I'm just skipping ahead a bit. You should know this by now. So 0.175 minus x, ignoring the minus x. So again, very repetitive at this point. Once we can get to that point. Now, what is x equal to, though? Well, x is equal to OH minus, not H3O plus. Remember, that's that mistake I said is quite common with these. So I'm multiplying there. I get that equals to x squared. Take the square root, and we get x equals 6.6 times 10 to the minus 5. Negative log of that, and we get a POH of 4.18, which gives us a pH of 9.82. So don't forget about the, I got a different answer on my answer sheet. Why? Oh, I wonder if I messed this up. Oh, I think I put in, so it should have been 1 times 10 to the minus 14. I don't know why I did 1 times 10 to the minus 11. So 1 times 10 to the minus 14 divided by 4 times 10. Maybe you're screaming at the screen. I think I did say that out loud. Yeah, so that changes that, which changes this to times 10 to the minus 2.09 times 10 to the minus 6, which gives us a POH of 5.68, which gives us a pH of 8.32. That's better. All right, so just a little math there. Okay, so now the next part of that then is, what about a combination of the two? We have the weak acid, HNO2, not the Na. We have NO2 minus, which is its conjugate base. So we have a buffer solution here. So we could recognize that as a buffer solution or not. Now this is where it starts to get tricky in terms of how do I write the equations? Because when you have a buffer solution like that, we don't worry about the NaNO2 when we write the reaction until we do our I, C, and E, because now we don't worry about water. Our initial concentration of the acid is 0.2. We don't have any HNO3, but we have added that common ion, so 0.175. So minus x, 0.2 minus x, and then ignore the minus x. Plus x, so we have x, and plus x, 0.175 plus x, but just like before, we're ignoring the plus x. So now I have the Ka. I'm just going to skip writing the expression. 4.0 times 10 to the minus 4 equals x times 0.175 over 0.2. And what we have right here is the Henderson-Hasselbalch equation if we take the negative log of both sides, which I will show you. So 4 times 10 to the negative 4 times 0.2 divided by 0.175, and x, which equals the H3O plus, is 4.6 times 10 to the minus 4. So the pH is the negative log of that, and we get 3.3. All right, so 3.3. So that's the way, that's solving it called the common ion effect method, where we're adding, this in the beginning, where we don't have two zeros. We still are going to proceed from left to right, though, because we don't have any of this yet. All right, what about if I recognize it now as a buffer, as you well should? So pKa plus the log of the base over the acid. So this is this part of that equation I talked about, taking the negative log of both sides and then rearranging it a little bit. So the pKa is the negative log of the Ka. That gets us 3.398. Just kept some extra digits, times the log of the base, 0.175, over the acid, 0.2. This is negative 0.06, and so our answer comes out to be 3.3. So 3.3 for the pH. Either way you do it, recognize it, do it the shortcut, do it the long way. Really up to you which way you want to learn it. I would say definitely both. If you're only going to learn one, though, you want the Henderson-Hasselbalch equation, not this way. All right, so look what I have down here now. So this is a graph of the titration of the volume of the titrant, which in this case is the strong base, let's say NaOH. And over here we have the weak acid, let's say HNO2. And what we have over here, though, is the pH of the solution of the mixture of the two. So in the beginning, we only have HNO2. So in the beginning, there's 0 milliliters of the NaOH. Notice what this reaction is. HNO2 plus NaOH. What it really is, though, is HNO2 plus the OH minus, because of that, again, that spectator ion. Well, what we have in the beginning then is if we, like question 2, where we only have the acid, the pH came out to be 2.05. So right here we have, 2.05. There's our initial pH. And then you start adding NaOH. Well, all along here, until you get to what's called the equivalence point, you have a buffer. So that's the buffer zone. Anything along there, we have the buffer. We're going to look at a specific spot called the half equivalence point. What the equivalence point is, this is the number of milliliters of base that we had to equal the moles of the acid. So in other words, the moles of acid equal the moles of base at this point. That's where the equivalence comes from. Moles of acid equal the moles of base, according to the balanced reaction. This is a monoprotic acid because we only have one equivalence point. Because remember, you would lose one hydrogen at a time. So if you have more than one hydrogen, you're going to have 2, 3, 4. The shape of the graph, you'll see, will be a little different. All right, so 0 milliliters until we added. So this equivalence point right here, you can see there's a really sharp, if I reset everything, a really sharp increase in the pH once you get close to that equivalence point. So the equivalence point is this really sharp change. Because up to this point, you can see the pH isn't changing very much. There it is initially, and until you get to this rise right here, you can see it doesn't change very much. But then you have this dramatic change. And it's the midpoint of this vertical line is what is referred to as the equivalence point. Notice the pH of this is greater than 7. It's not at 7. Why? Well, what do I have at the equivalence point? I have no more acid, because that's limiting. I have no more base, because that's the limiting. In other words, we have the stoichiometric equivalence point. So we only have the salt that is produced in water. Well, water is only going to affect the pH if the salt does not. In this case, it was Na from the base, and it was NO2 minus from the acid. Well, that's the one that affects the pH. And that was the calculation that we did right here in question 3. So question 3 is, what if you have only NaNO3 or NO2? So you have Na plus and you have NO2 minus. Again, that doesn't affect the pH. This is at the equivalence point. This is a calculation anywhere before the equivalence point once you start to add base. So the buffer zone. So anywhere along here, we can use pH equals pKa plus the log of the base over the acid. In the very beginning, we have acid only. And then at the equivalence point, we have the salt only. And then we'll deal with after. All right. So I definitely want you to try this. So those are the 9 of you that are going to be coming in here. We're definitely going to try this with an actual burette and, physically doing a titration. And then you'll see the joke of this. Okay. All right, so a titration is performed using a strong base, sodium hydroxide, and the weak acid, acetic acid. This is a very common one because acetic acid is vinegar. At the equivalence point, the resulting sodium acetate has a molarity of 0.3. So we're at the equivalence point, which means we have the salt only. There's no acid and no base. They're both limiting. So given the Ka, write all relevant chemical equations. So really, it's just more practice of the same kind of calculations we've been doing. So hit pause, give this a try, and then we'll move on from here. All right, so here comes. All right, so let me do the chemical reactions first. So write all chemical reactions that are relevant. So the first one would be, I'm adding the strong base, NaOH, with the weak acid, and the result would be glitch there. All right, so there's our reaction. Now what they're saying is you're at the equivalence point. So the moles are equal. And notice it's a 1 to 1 mole ratio. So the moles are equal. If it was a 1 to 2, you could still have the moles equal, but you would need twice as much of one or the other. So there's 0 of this left and 0 of this left. So all we have is this stuff. And that's what the reaction said. So we have the sodium acetate at the equivalence point. Now, what's the concentration of this? Well, it says it's 0.38. Well, it's going to give us Na plus and CH3COO minus. Well, the Na plus is the conjugate acid of the strong base, so we don't use that one. So we use CH3COO minus, we add it to water, and we get an equilibrium. You get CH3COOH, and you get OH minus. Sorry, not OH minus. Ice chart. The initial concentration was 0.38. We don't care about water, none and none. Minus X, 0.38 minus X, but we know we're going to ignore that. Plus X, X, and X. Notice we have an OH minus, which is a base, but we're given the Ka. So I need the Kb. Now, I'm going through this quickly, but this shouldn't be new. If it is new, catch up. That's the whole point of this. You have access to all of the answers from me. But you got to come and see me. So the Kb, all right, so 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, and we get 5.6 times 10 to the minus 10. So 5.6 times 10 to the minus 10 equals x squared over 0.38 minus x, but again, we're ignoring the minus x. So that number times 0.38, that's x squared square root. X, which equals the OH minus, is 1.45 times 10 to the minus 5. So when you take the negative log of that number, you get not the pH, but the POH at 4.8. And therefore, the pH is 9.2. Now, if I were to predict whether that original salt was acidic, basic, or neutral, I would have said it was basic because of the weak acid conjugate. Remember, it's always the weak one. So 9.2. Yeah, and it is a basic salt. It's greater than 7. All right, so try those ones I gave you today. Give them a try, and we'll pick up some more with titrations tomorrow.